This video is sponsored by CuriosityStream. Get access to my streaming video service, Nebula, when you sign up for CuriosityStream using the link in the description. Dark matter is the most mysterious substance in the universe, and also what most of it seems to be made of, and yet it may be the keystone of building future civilizations. Dark matter. We don't even know what the heck the stuff is, so it might seem hard to discuss technologies that make use of it. At the same time, we do know a few things about it with great certainty, and a few more with some confidence, and one of those is that dark matter makes up the vast majority of everything in this universe. Given that it does make up most of everything, finding ways to use it is likely beyond every civilization's wish list of technological advancements, and that's our main focus for today. How civilizations would use this hyper-abundant material if they could, and in what ways they might. For a type of matter that is apparently so common, it is rather irritating that we know so little about it, and we should probably start by talking about what we do know about it. First, it almost certainly exists. That irritates a lot of folks and often raises many objections. Some are reasonable objections, but some of those aren't terribly valid. As an example, we've never seen any dark matter directly, and that seems a good objection, until one remembers that we've never seen most of the Earth directly, including its mantle and core, and never hesitate to discuss its interior, nor the interior of our sun or any other star. We also don't see subatomic particles. They are smaller than light waves, and we detect them mostly by blowing stuff up and looking at the pattern of the wreckage to see what could have caused it, so to speak. So there are a lot of legitimate objections to dark matter, and we'll discuss some of them, and discuss more of them a few years back in our dark matter episode. But the ones hinging on us not being able to detect it directly are not good ones. Most particles we first detected were detected by indirect means, like picking up gamma rays to prove the mass of the electron and positron after a pair of them had collided and emitted those gamma rays. Generally, we've measured the mass of other atoms and their interiors by seeing how much other charged particles were deflected by the protons in their core when passing by them. Nor is the time argument a good one. Folks say we've been looking for it for a couple of decades now and still haven't found it, but that's not true. We haven't been looking for dark matter unsuccessfully for a couple of decades. We've been looking for dark matter unsuccessfully for over a century. We have all sorts of particles we hypothesized decades before we proved they existed, and considerably more we hypothesized and haven't found out yet or even ruled out. Dark matter has been bugging us a lot longer, since before we even knew what a galaxy was, what subatomic particles were, what two of the four fundamental physical forces were, or how those particles interacted with those forces or did not. Way back in 1884, Lord Kelvin estimated there had to be a lot more mass we couldn't see than we could see to explain the velocities of stars orbiting the Milky Way. He didn't assume any type of exotic matter at the time, just mundane matter not in stars, and that was the general notion for a long time. We just assumed it was various things which were normal but dark, like interstellar dust or planets, or later even stellar remnants. Indeed, that was one suspected culprit back in Kelvin's day, because we assumed stars gave off light from being formed very hot and slowly cooling, as we had no clue that nuclear fusion took place inside stars. Problem was, we did find a lot of this mundane dark matter, and it never even came close to adding up. In modern times, we know that virtually every galaxy we can see has a lot more mass than the stars we can see and account for. How do we know that? The calculation uses the fact that for an object in a roughly circular orbit, the centrifugal force on it is equal to the gravitational forces subjected to by the body it's orbiting. Since if we determine the distance to the galaxy of interest, we can use its angular size in our field of view to determine its radius. If we observe it over time, we can measure the speed of objects orbiting the galaxy's edge. From the orbital radius and velocity, we calculate the centrifugal force, which is equal to the gravity exerted on it, which tells us the mass of the galaxy. But when we use the starlight from a galaxy to determine the numbers and types of stars in it and add up the masses of those types, we consistently find that the luminous mass of most galaxies is only about a tenth of their gravitational mass. We can see the speeds of stars on the outer edges orbiting them, and we can see how much they pull on neighboring galaxies, and every alternative answer for it not being gravity didn't work out. Tons were tried. Well, then we had to ask ourselves what generates gravity. In point of fact, it isn't actually mass. Any type of energy generates gravity, but mass is one type of energy under Einstein's E = mc². And all the other types of energy except light-speed objects like photons are associated with mass. For instance, you can have an awful lot of kinetic energy on an object with mass, but for it to come anywhere near paralleling the amount of energy tied up in the mass itself, it needs to be moving at relativistic speeds. Galaxies are hugely massive affairs, but even they can't contain objects moving at those speeds for long. So your only two remaining objects are rotational energy of certain very dense objects like black holes, neutron stars, and white dwarfs, or the random kinetic energy of particles in very hot objects, again like neutron stars and black holes. Only a tiny fraction of stars end up as neutron stars and black holes, and all known stars combined won't add up to the missing mass, so it's not these stellar remnants, there just aren't enough of them. But it also means that missing energy generating all that gravity in galaxies has to be mass energy. Probably. We can't rule out some other type of energy storage besides the known 5, which are mass, kinetic, potential, thermal, and radiant energy. Dark energy does not fit the bill incidentally, that appears to be evenly spread throughout the universe, whereas the missing mass we call dark matter clumps in galaxies. This is also why we often say it has to be cold, which in physics terms and context means the individual particles or objects of dark matter can't be moving very fast or they would exceed the galaxy's escape velocity and not clump into galaxies. This overall motion is random and thus can be thought of as heat energy or temperature. Galaxies tend to have escape velocities on order of hundreds of kilometers per second, so cold is a rather dubious term here. Something with a velocity sufficient to escape a galaxy and the mass of a proton or neutron still has a temperature comparable to the inside of a star, in the sense of random kinetic energy being heat energy. That's nothing compared to relativistic hot temperatures though, and is a bit problematic considering we always assume everything in the early universe was ultra hot and cooled down by radiation and collision. A dark matter doesn't emit photons as heat radiation, and do not collide with anything, even other bits of dark matter, or do so very infrequently. Which is the other thing, what is a collision? Down at the atomic scale, the whole concept of a physically rigid object is out of play, it just doesn't mean anything. Collisions occur using those fundamental physical forces. Not every known particle interacts with all of those either. Electrons and their big brothers the muon and tau particles, along with their antiparticles, are what we call leptons, and they don't even notice the strong nuclear force that binds quarks together to make things like protons and neutrons. We have 4 fundamental forces. Quarks, and thus things made from them, interact with all 4, though many of those constructs, like the electrically neutral neutron, don't interact much with one of those. In the same way, neutrinos don't interact with a strong nuclear or electromagnetic force, just gravity, which everything seems to, and the weak nuclear force, and the latter so weakly that a neutrino could pass through a light year of lead and likely make the trip uninterrupted. Our best neutrino detection methods manage to nab the occasional one interacting with matter, while countless trillions will have passed through that same spot first. Neutrinos move at near light speed, within the tiniest fraction of a hair's breadth of light speed, and have only a smidgen of mass, less than a millionth of what an electron has, or a billionth of what a proton or neutron has, and a neutrino-antineutrino rest annihilation would produce an infrared photon, not the millions or billions of times more powerful gamma-ray photons those other particles produce when annihilating with their antimatter opposites. They carry far more energy though, and it's almost all kinetic energy. Neutrinos are not our focus for today. They are not dark matter, though they have been a popular suggestion in the past. But if you could make a thin foil able to absorb or reflect neutrinos, you would have a rather awesome solar sail, and if you could make the equivalent of a laser, a neutrino beam, that would be a great way to shove spaceships around, since it would mean a super powerful beam only handy for ship propulsion, not a giant doomsday beam like laser propulsion platforms would be if used for militant intent. The most popular suggested particle for dark matter these days is most easily thought of as something like a heavy neutrino. Neutrinos move at near light speed because they are created in events that typically kick out an electron and proton, or their antiparticles, at fairly high speeds, and the neutrino gets the same kick, but having vastly less mass, exits the event at a vastly higher speed. Imagine instead that such a particle had the mass of a proton or neutron and maybe even more. We do have some elementary particles more massive than them. 3 of the 6 quark types, charm, top, and bottom quarks, outmass protons and neutrons, the top quark by a factor of a couple hundred, as does the electron's big brother, the tau particle, and 2 of our gauge bosons, the W and Z bosons. The other 2 types of gauge boson are the photon and gluon. Gauge bosons are what transmit the fundamental forces, and the W and Z boson being supermassive is why the weak force, which they transmit, is so weak. which is to say so short range. They decay so rapidly they barely have time to carry the force anywhere. The Higgs boson also outmasses protons and neutrons, and by more than 100-fold. So of the current 17 elementary particles in the Standard Model, of which neutrinos are 3 incidentally, 7 of them are more massive than protons and neutrons, which are not elementary particles, and between the most massive, the top quark, and the least massive, the neutrinos, there is a mass difference of around 1 trillion. Keeping all that in mind, the idea that there's a particle as weakly interacting as a neutrino, but more massive than a proton or neutron, does not seem that far-fetched. These weakly interacting massive particles, called WIMPs, are probably the most popular category of candidate for dark matter, and will be our primary focus for technologies to discuss today. But they don't have a lock on the title for dark matter constituents. Not all of them require some new elementary particle. Many of these don't even require some unknown type or quantity of matter like machos, or massive compact halo objects, such as black holes or brown dwarfs, and we have extensively discussed how valuable black hole technologies can be in other episodes, though machos are not viewed as a good dark matter candidate at this time. However, mundane solutions other than new types of particles can still represent valuable knowledge for new technologies. Remember, one way or another something generates an effect that causes either a great deal more gravity than all the known mundane matter around, or alters a fundamental force like gravity or electromagnetism to operate other than inverse square at big enough distances. If such variations exist, they can probably be exploited for technology, such as reversing them so gravity was stronger at near distances, for instance. One example is MOND, Modified Newtonian Dynamics, which was suggested early in the 1980s as a dark matter solution by proposing that gravity only acted as an inverse square force, weakening with a square of distance, out to a certain distance, beyond which it got much weaker. This doesn't necessarily require magic either. Force-carrying particles can decay over distances. That is exactly why the weak force is so weak. The W and Z bosons decay before covering even atomic distances, let alone astronomical ones. So if the graviton had a half-life of 1 billion years, gravity 1 billion years travel away would be half as strong as suspected. There's an issue with that. A graviton would have to have some rest mass. Particles with no mass experience no time, and thus can't have a half-life, and gravity moves at light speed, which no particle with mass can do. But gravity is hard to detect, and the neutrino has a tiny amount of mass and moves within a fraction of light speed. As the theory suggests, so could a graviton, potentially being less massive and faster than even a neutrino. MOND had quite a following and had a fair few variations, but fell out of favor with the detection of the Bullet Cluster in 2006, a pair of colliding clusters of galaxies about 4 billion light-years away. We'll skip discussing why today, especially as there are some rebuttals, in spite of many folks saying the Bullet Cluster shot MOND dead. See the episode on dark matter for more of the suggested types too. I mention it because if you found out that gravitons had a rest mass and could decay, for instance, they might start implying ways to generate gravitons with lots of mass, or reflect or bounce them around, making a gravity laser or grazer, things like that. We are very limited in discussing technologies relying on matter or forces we do not understand, but this is what we can discuss today. Some are easy. If dark matter is any sort of particle that has mass but doesn't interact much, then if you can find something it does interact with, you can scoop it up and use it as a cheap source of mass. It would be useless as a building material, but becomes great not just for making gravity on artificial planets, freeing up not just valuable heavy elements but even hydrogen and helium for other uses. It also lets you do strange stuff, like create a big ball of dark matter with a deep gravity well, and yet so weakly interacting you could fly right through it. As an example, what happens if you dump around a stellar mass of dark matter into an existing star? None of that dark matter is getting blown away by that or sinking into the core, it just floats around generating gravity and minding its own business. The gravity it creates though would not, and would squeeze that star down even more, speeding up fusion. It is potentially handy as a fuel source too. Dark matter should have all the energy per unit of mass anything else does, so if you stuff it down a black hole it would work as a starship fuel. See our Black Hole Starships episode for discussion of how we can use black holes for ships and power. So we do have at least one known way to manipulate dark matter. It does react with gravity, and while it would be very hard to get it into a black hole, once over the event horizon it is as stuck there as anything else. It's hard to get in because black holes are small, So the only way it ever ends up in one is if by some freak chance it happens to run into the event horizon straight on. Normal matter can be sucked into an orbit of a black hole as more of it accumulates. The bits orbiting the black hole can start bumping into each other, getting hot and falling in. This is the accretion disk. Dark matter doesn't do that. If it gets into orbit around something, it will just keep orbiting, not clumping together. This is why dark matter in galaxies forms a roughly spherical shape, while the matter in galaxies tends to form more of a disk. But dark matter can be absorbed by a black hole, and we estimate there's a bit more than a proton's mass of dark matter per cubic meter of intergalactic space. Now, a 3 solar mass black hole, which is generally about as small as can naturally form, will have a cubic volume inside its event horizon of about 3 trillion cubic meters, and would have absorbed all that dark matter locally present. But that's only going to be about 4 picograms of mass, and even the big monster at our core, with 1,000,000 times more mass and 1,000,000,000,000 times more volume, would only have swallowed up about 4 tons of dark matter. Of course, the stuff is moving, not static, so it would be more than that. Let's assume we shot a black hole with a square kilometer of cross-section through a galaxy on a 100,000 light-year path, or 10 to 21 meters, or slicing a column through a galaxy of 10 to 27 cubic meters. We'd still have only swept out a couple kilograms of dark matter. You could throw on more sails, so to speak, by having a cross-section tens of thousands of kilometers across or even larger. One 10,000 kilometers across will sweep up dozens of trillions of tons of matter. Or deflect it or capture it for later use if we're talking about a material that absorbs dark matter instead of a black hole or an artificial event horizon. Collecting dark matter is not likely to be an easy task, but if you can do it, then it represents a vastly bigger supply of matter and energy than all of our mundane sources combined. It's also quite possible they're all dark matter-only interactions, such as dark matter-antimatter annihilation or dark matter fusion, that might only be possible when you squeeze this stuff in rather tightly. If you had 2 such beams, one dark matter and one anti-dark matter, when and where they collided might be a very energetic event. That might also be a terrifying weapon since dark matter would be hard to detect or deflect. And that's assuming it doesn't have other strange properties. Many proposed dark matter candidates interact strongly with space, time, other matter, or other forces. As a reminder, certain scenarios for dark matter would imply the ability to play with gravity more than we currently expect, and things like flat event horizons or gravitational scoops might be on the horizon at that point. Imagine for the moment we had some bit of clock tech that lets us stretch a black hole into a disk, like it was some balloon we could squish flatter. Now that implies the ability to manipulate gravity since it didn't radiate omnidirectionally, but let's say we could, either flattening the gravity out into a disk or squishing it into a pair of polar jets. See our anti-gravity episode for more discussion of gravity-based technologies, but such manipulation might let you have a spaceship that could suck in matter, even dark matter, as it flew by. That's also a potentially potent weapon and shield too, though it should be noted that anytime 2 event horizons touch, they will merge to an external viewer. A black hole event horizon has a radius proportional to its mass, and a cross-section proportional to the square of mass, so you can make really enormous black holes and get dark matter that way, and presumably an awful lot of dark matter will get absorbed in the post-stellar era of the universe, as you start having all the other matter get sucked into black holes, all orbiting each other and perturbing everything else orbiting, including dark matter, till it combines together or gets ejected into the extragalactic void. Of course, that scenario would tend to imply you didn't have little bits of physical dark matter lying around in favor of something like Mond, but it's also possible the solution to dark matter will turn out to be 2 different effects, which is to say we have problems pinning down what dark matter is because our predictions keep missing, and they might do so because it's 2 overlapping and unrelated effects that amplify a given net effect we're seeing, as in we do have WIMPs and we do have decaying gravity, but fewer and less of them. You would need to have some way to manipulate this stuff, but if you do, it's very useful, probably with valuable properties we don't even know about. You might be able to make unique materials out of it, but in space where things are quite empty, it's nice to have something to push against, but only when you want to. Neutrinos and neutrino-like particles, weakly interacting particles, if you have something that can interact with them more strongly, it lets you use them, potentially selectively, to interact when you want. When flying through space, I want to interact with nothing, except for when I do, like for slowing down or turning, so we often contemplate unfurling reflective solar sails or magnetic fields to interact with solar wind. Ones able to work with neutrinos, or neutrino-like types of dark matter, would be useful for the same reason. Dark matter is not dense, but with a big enough sail you'll hit some, and the momentum exchange is going to be based on your speed. Also, if these are particles, it may be possible to build something out of them if we understand them better. On the flip side, the ability to mimic the weak interaction or non-interaction can be handy. We often see force fields in science fiction as a means of defense, but the other popular method tends to be totally invisible or ethereal, so you either couldn't be seen or things went right through you. In practice, that has to be both, since folks can only see you if light bounces off you, which means a laser beam would bounce off you too, or more importantly, would vaporize you. If I can see you, I can interact with you, and if I can interact with you, I can hurt you, or use you to hurt someone else. But if you can make yourself unable to interact or be interacted with, that's a very good defense. And if you can make your ship or space station have that weakly interacting property temporarily, or even build out of dark matter, that's a very good method of both stealth and defense. As an example of weaponizing WIMP-style dark matter, you could probably put a cloud of it around someone's planet as a way of keeping them earthbound, positioning it either to raise the surface gravity or to make a cloud in circular orbit over the planet, so the surface gravity stayed the same but the escape velocity was arbitrarily high. So you could wrap that planet so thick in dark matter that time slowed down on it and only relativistic spaceships could leave. A good way to quarantine a worrisome species you didn't want out in the galaxy but didn't want to interfere with or destroy, a situation reminiscent of the people of Cricket from Douglas Adams' novel Life, the Universe, and Everything. So we talked about spaceships and power, and again it's a great power source simply as raw material we can feed into a black hole that is abundant and not useful for other things, assuming of course we can find a way to gather it. However, same as we discussed filling shell worlds up with hydrogen or black holes to generate gravity, dark matter offers us that same route. We don't know much about it, but we know it doesn't interact much, even with itself, so we should be able to cram this stuff together quite tightly without the normal pressure issues. We normally say if you want gravity on something small, without using spin gravity, you need micro black holes, but ultra-dense dark matter might be an option too, squeezing tons of it into a volume the size of a pinhead. It's going to act very differently than normal matter in a lot of counterintuitive ways. For instance, if you had a solid block of stuff cooled down to ice cube temperatures and threw it in a pot of boiling water, it would not heat up. Partially because it would fall right through the pot, but if that pot were lined with whatever your hand was covered in to toss it in, then the ice cube of the dark matter could sit in that boiling water for eons and pick up no heat from the water. It would also bounce up and down on the bottom of the pot over and over again unaffected by the water. Same, dark matter could fall through the pot and the earth and fall through the center and right back up again, then down again over and over. If you got something you can sheath it in, that it does bounce off of, then you could be making ultra-dense and heavy objects, which is very handy for certain more abstract megastructures where you want gravity lower or higher in certain places. Unsurprisingly, its use as a source of cheap mass appeals to me for world building, and that might bias me toward the WIMP version of dark matter, but other versions would have their uses too. Some dark matter options include particles that interact with gravity and some unknown fifth force. If that force only interacts with dark matter, we wouldn't even see it, except in its tendency to draw dark matter together, but not very much. This has some problems. For instance, it can't be too strong, or, since dark matter does interact with gravity, that fifth force interaction would allow more clumping and result in giant black holes all over the place. We also tend to assume dark matter, if a particle, would have an antiparticle, and when it annihilates it obviously doesn't produce photons as most commonly happens in matter-antimatter annihilation, as we would notice that. Unless it does so at the 1.9mm range, that of cosmic microwave background radiation, which is unlikely and would really mess with our current cosmological models. But it might annihilate into some other form of energy too, for instance dark energy, which causes bits of new space to emerge all over the place. I often make a point of telling folks that in spite of the similar name and extreme abundance, dark matter and dark energy don't have anything to do with each other, that we know of anyway. And there are a few dark matter theories that do tie it to dark energy, such as GIMPs, gravitationally interacting massive particles, which some folks feel fit better with the vacuum solutions to Einstein's equations for gravity, the basic notions being bits of dark matter were singularities of dark energy. As I mentioned earlier, it's not mass that generates gravity, it's energy, and mass is just the easiest dense form of it, and so you can make a black hole or singularity out of any very dense clump of energy. Cram enough photons in one place fast enough and you'll get a little black hole. So presumably cram enough dark energy in one place and you get a singularity too. Though given that dark energy's only known property is its association with expanding space, I wonder how you would cram it together. But it might be crammed together initially and decays, as we expect small black holes to do, and causes space to emerge when it does. Primordial black holes is another popular dark matter option. The early universe was super dense, and black hole formation without a supernova implosion, or even bits of energy that never expanded in the first place, are certainly plausible options. One issue with that is that we think black holes decay, and the smaller the faster. That's Stephen Hawking's original famous contribution to physics. It is only a theory, there is no experimental proof of black hole evaporation. Assuming that is right, then a primordial black hole could not mass less than 10 to the 11th kilograms, 100 megatons, or they would have evaporated by now. Now this means none of them could be, or we could see the radiation of their evaporation all over the place. We don't know that primordial black hole mass will be evenly distributed, with some massing a ton, some 100 tons, and some 100 billion, and all points in between. But we do know it can't be evenly distributed at masses below 100 megatons unless our concept of black hole evaporation is wrong. Otherwise we would see radiation being emitted corresponding to those black hole evaporations. There are a number of other issues with primordial black holes as dark matter, and the option, like MOND, is less popular these days, but if true it would make for a great technology, see our black hole episodes for why. But there's more problems there too. First, if black holes do not evaporate, then they become eternal traps for matter, though we can still generate power with them by dumping matter into them, though it is hard to put matter into a micro black hole. However, they should be able to absorb matter rapidly inside something like a neutron star, and were that the case, the larger ones, in excess of 1 trillion tons, would be able to capture mass in a neutron star, and ought to cause detonations of them that we are not seeing. Indeed, all things included, it's really only black holes in the 10 to 500 gigaton range that would have a decent chance of not leaving various other telltales of their existence we're not detecting, and we don't know any reason why primordial black holes would have formed in that mass range but not in others. Of course, we don't know why all the various subatomic particles come as specific masses either, like 511 kiloelectron-volts for the electron, so primordial black holes might do so for the same reason. Assuming they did though, and were our dark matter candidate, they would potentially be very handy. The ones on the higher end could be force-fed matter to make them bigger, but the smaller ones, at 10 gigatons, would give off about 3.6 megawatts of power, and do it for quadrillions of years, while those on the higher end, 500 gigatons, would give off 1400 watts, and for even longer, nearly 1 billion trillion years. Because of their sheer mass, they don't make for good starship drives, but would be great for stationary places, and indeed you'd probably just build around such medium-sized primordial black holes as you found them. We would also hopefully be seeing them in the future by getting better at detecting background radiation they would be giving off universe-wide, and isolating from other known sources like the CMB. Fundamentally though, the real power of dark matter probably won't be for power generation. That's just something that seems a probable use based on what little we know. As a last example, one of the candidates for dark matter is that it isn't crunched down mass or even energy, but crushed down dimensions, and both additional space dimensions and additional time dimensions, and if that were true and became something we could work with, opens up all sorts of scenarios like storing time, manipulating time, and maybe even twisting or ripping space-time. Fundamentally, the more we learn about dark matter, the more we can explore what we might do with it. But I hope from today it becomes clear why wanting to find out what dark matter's properties are is about more than just answering a big question about what the universe is made of. It's about recognizing that anything that abundant is useful simply in its abundance, and that its sheer mysterious nature implies properties we might be able to use for goals as mysterious and massive as dark matter is itself. One of the things we were discussing today was how even though we cannot see dark matter directly, we can still know it's there in much the same way we know what the insides of atoms, or our planet, or our sun looks like. It reminded me of a topic in a similar vein folks often raise, and that's if mathematics is a real thing or something humanity made up. Is math invented or discovered? And my friend Jade from Up and Atom, who we previously teamed up with to discuss Boltzmann brains and the anthropic principle, recently released a Nebula original addressing if math was invented or discovered. She is one of a number of science and education creators we teamed up with to form Nebula, our Streaming Award-nominated streaming service, a little over a year back, and it's exploded since its inception, allowing us to invite in more creators and get a bit more ambitious with original content, like our Coexistence with Aliens series, It's also where you can watch episodes of SFIA a couple days early and ad-free. Now you can subscribe to Nebula by itself, but our friends over at CuriosityStream, which is home to thousands of top-notch science and education videos, have teamed up with us to offer Nebula's content along with their own if you sign up at the link in the episode description. That means you will not only get CuriosityStream and get to see their excellent shows like Space Phenomena's episode on black holes, but can also catch SFIA episodes early and without ads, and help support our show while you're doing it, as well as seeing amazing exclusive content from our sibling shows. Again, you can get a year of both CuriosityStream and Nebula for less than $15, get to support the show and see our episodes early, and get all of that for less than $15 by using the link in the episode's description. I also want to thank everyone who's been supporting Nebula, and for those watching the episode there, I was just expanding on some of the improvements we're making and planning and how much fun it is to get to interact with so many other creators. I've heard some horror stories of working with various artists or actors over the years who were monstrously egotistic or hard to work with, so I'm always pleasantly surprised by how fun and down to earth just about everyone I've met has been, from smaller shows all the way up to the giants 10 times our own show's size or more. 2020 was a hard year for a lot of folks, and some creators did end up tossing the towel, especially those with newer channels still in growth phase. I know in some cases it was from funding drops, so while I'm thanking the folks supporting us on Nebula, let me also thank all our Patreon subscribers who stuck with us through the crisis, and the recent reshuffle on that platform. This channel literally would not exist without you, nor would countless other shows. So this weekend we have another SFIA Sci-Fi Sunday episode, where we'll be examining the notion of alien cohabitation, and we will discuss both the structures meant to support multiple alien ecosystems and the relationships we often see in science fiction, of aliens and humans marrying and having hybrids, on Sunday, February 14th, Valentine's Day. Then next week we'll be looking at orbital bombardment as we return to our space warfare series, before closing the month out with an episode on colonizing giant stars in 2 weeks, and our monthly livestream Q&A on Sunday, February 28th. If you want to know us when those and other episodes come out, make sure to subscribe to the channel, and if you'd like to help support future episodes, you can donate to us on Patreon or on our website isaacarthur.net, which I'll link in the episode description below, along with all of our various social media forums, where you can get updates and chat with others about the concepts in the episodes and many other futuristic ideas. You can also follow us on iTunes, SoundCloud, or Spotify to get our audio-only versions of the show. Until next time, thanks for watching, and have a great week.